relational databases. I'm going to try to cover the most important concepts, but if at any point you have any question, please just interrupt me. Please interrupt me. So, for that, I'm going to just we are going to try to design a database for a transparent public bank. This bank has all of its information visible to the public. We try to make this bank secure and just efficient. Okay. So, what do we store in this bank? Just transactions. Who sent how much to whom? That's it. We just store the transactions to keep track of the balances, and we make sure that nobody spends the money that it doesn't have. Okay? And it's like, ACH transfers, Venmo, just transfer of money. So one way to store the data and to make the database is just make one table, a spreadsheet. So this is our first attempt. So we store the names of the people, the account holders, and their balances, and the transactions for each person. Okay? And of course the address of each person. So this is a very simple model, a simple kind of database, just one table. But it has some problems. So in the transactions column, we see that each cell can contain multiple entries. Essentially, what we have here is a table inside each cell. We have a table of tables. That can cause several problems. For example, if you want to find a specific transaction, you have to find the person and then go to the list of transactions for that person and find that transaction. And imagine if the person is involved in like 1,000 transactions. And also, we should match the transactions from both sides. So if Marcus sent some money to Sarah, Sarah should have received that money from Marcus. So we should make sure that it is consistent. Okay? We have some redundancies here. And redundancy can cause discrepancy. Redundancy can cause discrepancy. We want to avoid redundancies as much as possible. So this is not a good design. In technical terms, they say that it violates the first normal form. It violates the first normal form. Our goal is to design a database that complies with the normal forms, including the first normal form. Okay? So, now I should mention that when I say column, it's the same as variable, it's the same as field, it's the same as attributes. So, they are equivalent. On the other hand, record is the same as row and the same as unit. They're equivalent. Okay? So now our second attempt. Let's organize the data like this. We have a lot of data. Let's put the transactions in the table. So for each transaction, you have the sender, the receiver, the amount that is transferred, the address of the sender, the address of the receiver, etc. Okay, so now we are complying with the first normal form. No cell has multiple values. Each cell has just one value. However, what we have here is that in some cells, so for example, for the address, what we have is that we are storing the address of each person every time that the person involves in a transaction. So if a person is involved in 1,000 transactions as a sender or a receiver, we are storing his or her address 1,000 times. That is also a redundancy, and that can cause several problems. They call them several anomalies. For example, updation anomaly is one of them. If I want to update someone's address, I have to go to every transaction that this person was involved as a sender or a receiver and update that address in every transaction. So that's ridiculous. That's going to take a lot of time. Also, it's going to take a lot of space. We are repeating the address of each person several times. So in technical terms, they say that this is not complying with the third normal form. We are violating the third normal form. essentially we want our database to comply with all the normal forms, first, second, and third, and there are more normal forms which we do not discuss here. But what can we do? So an idea is that we break down this table into two tables. So we have a table for the accounts. So instead of people, I'm going to say accounts. So we have the account number for each person, and we have the information about each person, like the address, date of birth, balance, every information that is related to that person, that is specific to each person. Okay? And that's it. We have a table of accounts. By the way, we have account number here because it is possible that two people have the same first name and last name. So we cannot just rely on the names to differentiate between the accounts. So we use the account number to make sure that each account is separate and different from each other. And then we have a table of transactions. In the table of transactions, of course, we have the sender and receiver. So we have the date of the transaction, the amount that is transferred, for sure, because the amount that is transferred, not the balance, the amount that is transferred is specific to each transaction. Okay? And the sender and receiver. But it is important that we do not need to store the information about the sender and receiver in this table, because it is enough to know the account number of the sender and the account number of the receiver. And then, if we want more information, we can look them up in the other table, the accounts table. Okay? So we do not need to repeat that information here. So we end up with two tables. So if we need some information in the accounts table, we just go here. If we want information about a specific account number, just go to this table and we see we have access to all that information. So when we are designing a database, like we are doing now, we do not care much about the contents of the tables. We do not care much about the rows. We want to focus on the columns and the variables. That's the design is most concerned about. So what we do is that instead of this view, we view the tables in the design view. In the design view, the rows are actually columns. The rows are actually columns. And the columns are the properties of the columns. So the columns specify the names of the columns and the data types of the columns. For example, account is an integer, of course it's a number. First name is text, balance is big int. So balance is money, and we could use decimal or float, double or something. But to avoid complexities and decimal points, I use just big int. And let's say we store the balance in cents, 100 times the balance in dollars. Okay? So we do not need decimal points. And the other information. There is also one important thing here, PK. PK means primary key. And that means this attribute, this column, is the primary key of this table. This column is the unique identifier for the rows in this table. So for every table, in every table, we need a primary key that can help us uniquely identify each record in that table. So the primary key is unique. For every row, it is different, and every row should have it. It is unique and universal. And that's it. So we have a table here. The name of the table, we usually use plural nouns. I usually use plural nouns for the names of the tables, and the name of the columns or the variables can be just lowercase nouns. So one important thing here is that some of this information may not be necessary to be stored in the database that we are building for the bank. So remember, this bank is public, it's transparent. All of its information is publicly visible. So do we want people to see the date of birth of our customers, or the social security number, or the Even the first name and last name? Probably not. So, we are violating the privacy of our customers. And the password, that's ridiculous. It's going to be useless, if it is publicly visible. So probably we should just remove these variables from our table and simplify our table. So the only information that we need is the account number, the balance probably, the time that it was created, and the public key. So what is public key? We cannot store the password, but we store something that can verify the password. So the user has the password or private key, and the public key is like a formula that can verify if the password is correct when the user uses the password. Okay? It's just a password verifier. That's it. So, what was the transaction table? Again, we need the design view. And in the design view, we have the rows as columns. So the columns will be rows in the design view. And we have the transaction ID as the primary key. It is the unique identifier for the transactions. And we have the date of each transaction. We have the sender and receiver. Of course, it is going to be the account number of the sender and the account number of the receiver. Okay, so it is int, therefore. And of course, the amount will be big int. It is money again. And that's it. We have the transactions table. So there is a new notation here. What is it? See a new notation here. FK. So what is it? What is FK? It's foreign key. So foreign key means that this column or this variable is actually a primary key in another table. Okay? So this variable essentially is pointing to a row in another table. So how does it point to the row in another table? With its primary key. So it's the account number. It points to using the account number, it points to an account in the account table. Okay, that's it. This is the meaning of the foreign key. But we are missing something here. In this case, we have only 2 tables. Okay, but what if we had like 50 tables, 100 tables? How would we know which other table the foreign keys are pointing towards? We have to specify what are the other tables, what are the target tables for the foreign keys. We have to specify that somehow, okay? Because it is not clear here. So for that we need a notation. We call that crowfoot notation. Specifically, this is the cardinality notation. The first symbol means that each record, or one record from the other table, is associated with only one record from this table. Okay. The next symbol means that each record from the other table can be associated with multiple records from this table. That's it. So, using these notations, we can connect the 2 tables, and we can see that the sender foreign key is pointing towards the accounts table, and the sender can be just one account. It is always the case for foreign keys, because a foreign key should point to one in the other side, one primary key, because the primary key is unique, On the other hand, an account can be involved in multiple transactions as the sender. An account can be the sender in multiple transactions. I can send money to multiple people, right? And the same for the receiver. So, what does this mean here? Can you tell me? This one. What does this mean here for the receiver? We are connecting the receiver as a foreign key to the account table. What does this mean?
One specific receiver.
Each transaction can have only one receiver, right? So, and on the other side, we see that the accounts goes to the transactions. Yes. What does this mean?
Can I ask you a question?
Sure.
So you said earlier FK means foreign key, right? And
Yes.
foreign key is primary key in another table, right?
Correct.
But I don't see sender or receiver as primary keys in any of the table, and why is that?
So it is actually the account number of the sender. And the account number is the primary key in the accounts table. So when I am pointing to the accounts table, I am pointing to the using the primary key of the accounts table. So we didn't name it the accounts. We could name it accounts, but we just named it sender, but we named the account number of the sender. So it is the primary key in the accounts table. But that's a very good question.
But why? How can you use different name? How would they know?
It doesn't matter. We know that when we see the FK here, we know that it is a primary key in another table. So we know that it is pointing towards the primary key in another table. Okay? So the sender, this number is pointing to the account number in the accounts table.
So there are two different tables in the database, and we know their connections, but how can a database system know the connection between those two?
Oh, so the computer knows the connection with this foreign key. So I'm going to show you the code. So the computer knows that this references which table. That's it. And this, we don't need these diagrams for the computer. The computer, this will be coded as reference. Just reference which table. That's it.
We have So by the way, I'm asking questions as if I'm still not.
Yeah,
understand.
that's good. That's
You
good.
know why? But those are the type of questions that students would ask.
That's great.
What you present. So we also have a question. And Anita.
Pirate.
I have a question, thank you. So if I want to know more information about that sender and receiver, I see that you've got connected to accounts, but there's nothing in the accounts table that gives me information about the sender's name, the sender's home address, the sender's, etc. So how do you take care of that information?
Oh, so actually we deliberately removed that information from our database because we think that it's not necessary to include that in the database. So this bank is publicly visible. All of the data is publicly visible. So whatever information we store anywhere in the database will be publicly visible. So we only store the necessary information for the transactions, and the necessary information.
But if I'm looking at a different company that's not public, I may have that information stored somewhere, right?
Exactly. So if it is not public, we can store the name of the person, address of the person. All the information can be in the accounts table. Yes, exactly. That's a good
Okay,
point.
thank you.
Sure.
Thank you.
So we have So what we did here was that we established the foreign key connection. So just to remember this, whenever we have a foreign key, so what we do is this sign, this crowfoot sign, and this always goes to the foreign key. This always goes to the foreign key. And it looks like an F, you see? It looks like an F. So the F always is plugged into the F. So, so you should remember that in one-to-many relationships, it is the case. It is just for you to remember, but I should mention that the actual constraint is the other side. The foreign key points to one row, one record on the other table. The foreign key is actually just a constraint. The foreign key is that the values for this column can only be from the values from this other table, from the values of the primary key in this other table. So it's just simply a constraint, nothing else. It is limiting the values that this column can take, the values that this variable can take. And that's what we want. We want to limit ourselves because we want to prevent errors. That's the whole point. We want to prevent errors by preventing redundancies and preventing can be correct. So what we saw was two one-to-many relationships. Just to make sure you understand, I'm showing them in the data view as well. So a one-to-many relationship means that a record from one table can be associated with multiple records from the other table. But a record from the other table can only be associated with one record from the first table. That's a one-to-many relationship. Now, I want to expand on the notation that we have, the Crowfoot notation, and complete the Crowfoot notation. In addition to the cardinality, we also can include the ordinality of the connections, of the relationships. This first symbol means that one record from the other table is associated with one and only one record from this table. The second one indicates that one record from the other table can be associated with no record from this table or one record. And the third symbol means that one record from the other table can be associated with one or many records from this table, at least one. And this symbol means that one record from the other table can be associated with no record or multiple records from this table. So now we completed our Crowfoot notation. Let's redraw our database. As you can see here, we have the sender pointing towards one and only one account. That means a transaction can have one sender and should have one sender. Okay, the minimum and maximum. The same for the receiver. The transaction can have one receiver and should have one receiver. The other side, an account can be the sender in one transaction, many transactions, or no transaction at all. Someone may send no money to nobody, right? A stingy person. So that's what it means. And the other side, what does this mean? Can someone tell me what this means?
Zero.
An account, no, an account, what this means here for the receiver. What does this symbol mean for the receiver?
It means they've either gotten lots of money or none.
That's actually a good point. That's very, that's good. So an account can receive no money from no one, or can receive money from multiple people, right?
I have a question.
Sure.
If we have an account that has not sent any money and has not received any money, why would we have it?
It may send money in the future. It may receive money in the future. And actually, in the beginning that we create the account, it is not involved, it has not been involved in any transaction. So in the beginning, every account has 0, 0. Okay.
Because we have to write it down first.
Yeah.
We have to record it, but
We have to create the account first before we can involve it in any transaction.
So, if I can ask, so you talk about when they can create an account even though it doesn't have any transactions, but what happens in the future if they decide to close the account or not have the account anymore? What happens in that situation?
So they cannot close the account because there are transactions that involve the account. So they can just stop using the account, but they cannot delete the account because there are transactions that they have been involved. So they cannot delete the history of the account. They can just stop using it.
Can I have lots of primary keys?
In one table,
Yeah, why do I have to have account or transaction ID? Can I have multiple?
multiple primary keys? That's actually a very good question. Yes, you can, but we have to talk about it. So any attribute, any column that is unique and universal and stable is a candidate key. That means it can be a primary key, but we have to choose. We have to choose one as a primary key. Okay, but we are gonna touch upon that. Okay. So now,
Anita, I have a question. Anita?
I want to go back to Robert's question. So if I have an account that's no longer being used, you said that I don't want to delete it because it could have transactions in it. So I'm going to press you to tell me why that's important if it has transactions in it, but it's not going to have transactions in the future. Why does that mean I need to keep the account?
So what you can do, that's actually a good question. So in any bank, when you open an account and you have had transactions, you cannot delete your account from the bank. Even when you close the account, you just stop using that account number. But the record of the account, transactions that the account has been involved in, all of them stay there. So, it's important, if you have sent money to someone, okay, that someone is also involved in that transaction. So you cannot just erase the transactions. If you erase the account, you are going to erase the transactions. However, what you can do is that.
So I basically need it for historical data or an audit trail?
Exactly. You need it for history, but you can delete the public key of the account. Okay, let's say, or you may just even forget your private key. If someone forgets their private key, so they lose access to the account. They lose access to the account if they forget their private key. And or if you delete the public key, so the person doesn't have access to the account anymore. So that's the only way.
Okay, thank you.
Yeah, sure.
This is the type of question a student would ask me. Is a public key a key?
In this case, so it's actually important. It is just a coincidence that we have public key and private key, naming they have key in their names, and here we have foreign key and primary key. It is just a coincidence. The key means different in for different things.
How is it different?
So public key, we mean asymmetric encryption. We are referring to asymmetric encryption by key. Okay, we are referring to hashing and things
It's like a password.
Yeah, we are referring to that side. But when we say primary key and foreign key, we are talking about the database tables and how we identify the rows in the tables.
That's just definitely the kind of question a student would ask me. They'd see key
Yeah,
and they'd be like, I don't know what a public key is. Why is that there?
So I'm going to just expand this design. We are going to switch gears, and then I'm going to just improve this design to include other types of transactions as well. So our design is too simple. Each transaction can have only one sender and one receiver. That's not always the case. For example, imagine you have roommates and you want to pay rent. So you pay rent together at the end of each month. You have one receiver, the landlord, but multiple senders, the roommates. So technically, practically, it is possible that a transaction has multiple senders. And we have to incorporate that into our design. So essentially, we have a many-to-many relationship between the transactions and the accounts, right? So each account can be a sender in multiple transactions, and each transaction can have multiple accounts as a sender. And that's easy to establish this many-to-many relationship. You can just put this many side on both sides, right? And of course, this always goes to the foreign keys. So we have one foreign key on this side and one foreign key on this side. Easy peasy, right? Right?
Can you?
No. Wrong. It is not. It is not.
Correct us.
Good hand. So the problem is that the foreign key is a constraint. The other side of the foreign key should always be 1. And the other side should be 1. So this is impossible. So how can we establish a many-to-many relationship? We can never have foreign keys on both sides. Okay? Always one side is the foreign key. So to have a many-to-many relationship, we need help.
Can I ask you a question? So when you say it is impossible Like conceptually, or is it impossible, like technically?
It is impossible conceptually, not technically. It is because this means that a transaction has one sender and an account has one transaction. Essentially, what we have here is a one-to-one relationship in this design. What we made here is a one-to-one relationship because a foreign key here is connected to a foreign key here. It is not good. We cannot have that. So it is not what we want, essentially. So to establish a many-to-many relationship, we need help. We need a table in between. We need an extra table. We call it a bridge table. You see, it looks like a bridge. This bridge table connects the transactions table to the accounts table. And I should mention that when we want to establish a many-to-many relationship, we use a bridge table like this. So both foreign keys reside in the bridge table. Both foreign keys reside in the bridge table. Okay? Say it with me. Both foreign keys reside in the bridge table. Like this. This is the bridge. Okay? Just remember this. You will never forget it. So this is the bridge table. It has the transaction ID as one foreign key and the account number as one foreign key from the account statement. Okay? So what does this one-to-many relationship mean? This simply means that each account can be the sender in multiple transactions. What does this mean? It means that each transaction can have multiple senders. Okay? Each transaction can have multiple senders. Multiple senders here. And of course, it should have at least one sender. At least one sender. But an account does not have to be at least in one transaction. No. So now the in amount is a new value that we have here. In amount is the amount that this account has contributed in this transaction. Okay? The amount that this account has contributed in this transaction as the sender is the in amount of that account. And of course, the signature is the signature of the sender, the account. Okay? So we are missing something here, something very important. Can you spot what is missing here? So remember, I said every table must have a primary key. Where is the primary key for this table? It doesn't have a primary key yet. So we can add a new attribute, a new column to it, and use it as a primary key. We call it a surrogate key, and it's just an integer. That's one solution. The other solution is to use the combination of the foreign keys as the primary key for this account. We call it a composite primary key. So why can we do that? We can do that because the combination of the transaction ID and the account number is always unique in this table. Must be unique in this table. In every bridge table, the combination of the foreign keys is unique. Must be unique. Because while each transaction can have multiple accounts as a sender, and each account can be the sender of multiple transactions, each account in each transaction can be the sender only once. So let's get back to our example, paying rent. So when I pay rent to the landlord each month, so when I pay rent in a month, I pay rent only once. I make my contribution of the rent only once in that month. Okay? So the sender and the transaction, the combination, would be unique. It happens only once. An account can participate in a transaction as the sender only once in a specific transaction.
Yeah, I have a question. It seems like we've overcomplicated it for no reason. Because if we're all roommates and we're going to pay you rent, why don't I just pay you my portion and Dan pays you his portion and Ali pays you his portion? Why do we need to combine that before we send it?
Yeah, of course, you can do that. So I did that example just for illustration purposes.
Okay.
Of course, it is possible to get around it. So the total amount is the sum of the in amounts for that transaction. Okay? So, and of course, the receiver receives the total amount. Because we have one receiver. Do we always have one receiver? Maybe not. It is also possible that we have. It is also possible that we have multiple receivers. So, for example, you pay rent. You also need to pay for electricity, for gas, or what else? Do you have internet here? I'm just kidding. Of course you have internet. So, since these two tables are very similar, we can combine them. Technically speaking, merge them into one table. And we should always do that. In the database, we do not want redundancy, not in the data and not in the design. We do not want to repeat similar tables. So if we can combine the two tables, we should. So instead of the separate tables for senders and receivers, we have just one table for the parties. Okay? And the amount can be positive or negative. For the senders, it will be negative. For the receivers, it will be positive. Because for the receivers, it increases their balance. For the senders, it decreases their balance. That is the convention that we can use. Let's do this. And the signature is something for the senders, and it's going to be null or empty for the receivers. We do not have to fill out every column. We can keep it just empty for the receivers. So we have simplified our database. We have a beautiful database now.
So repeat again, how do you know the difference when you talk about the parties? How do you know the difference between senders and receivers?
Amount. The amount can be positive or negative. So it is the amount that you contribute, you gain from the transaction. So you gain negative amount or positive amount from the transaction. Because it is your participation in the transaction.
You said that when tables are similar, that we always merge them.
We always try to merge them. The transaction fee, this is also unnecessary because we can calculate it. We don't need it. So when I sum up the amounts, I'm calling the amounts UTXO. I will tell you later. But UTXO would be the amount that is positive for the receivers and negative for the senders. And sum of the amounts, negative of that, would be the transaction fee. So it is computed. So it is essentially a derived field. A derived field is a field that we do not store. We just compute it dynamically with the function. So here, instead, we have a function.
Just ask from a student's perspective. So all the transactions, most of the transactions were in your parties table, and you only have the transaction fee in the transaction table. So why can't I move the transaction fee into that party table?
Let's say I put the transaction fee here for the parties. The transaction fee for all the parties involved in the transaction will be the same, right? Because they all paying the same transaction fee together. So for 10 parties that are involved in the transaction, it is going to be the same. And that means the transaction fee does not depend on the party and account together, but it only depends on the transaction ID, part of the composite primary key. It only depends on part of the composite primary key, not the whole primary key. That means we are violating the second normal form. So if you were curious what was the second normal form, that means the second normal form is no partial dependency. Each column should depend on the whole composite key, on the all composite key. So we cannot put the transaction fee here. We cannot put the balance also here. If we put the balance of the account here, it would depend only on the account, not on the transaction, right? So we only put the things here that depend on both the account and the transaction. Okay? Another derived.
So So this then assumes that they're all paying at the same time.
So they are paying, yeah, they are paying at the same time. Yeah. Kind of. They don't need to pay at the same time. So they're putting their money, and the transaction happens at once. So money is paid and distributed.
So it just like stays in that little party box before it goes on?
Yes, that is exactly what happens. Technically, that is exactly what happens. In the code, it is what happens. So another derived field would be the balance. You can technically calculate the balance, compute the balance for each person based on their ins and outs, how much they receive and how much they send. So this is also a computed field that we can calculate dynamically. Another thing that I want to add here is that the category for the transactions is not very helpful. And probably it's going to violate the privacy of our customers. So to organize the transactions better, instead of category, I'm going to use blocks. I'm going to put the transactions in blocks. And we put the block ID for each transaction to specify which block the transaction belongs to. So each transaction belongs to one block or no block. Of course, when we create the transaction initially, it does not belong to any block until it joins a block. And each block can have one transaction or multiple transactions. Of course, when we initially create the block, it has no transaction in it. For the blocks, we can include some other information to make sure that this database is tamper-proof. So remember, this is a publicly visible database, and we want to make sure that this database is secure, we enforce integrity, we should make sure of that. So we store the hash of the block in the blocks table. This way, if anything changes in the block, the hash of the block, the hash of all the information in the block, of course, changes.
Like blockchain.
So just
No, that's what they're gonna do. They're gonna get excited. They're gonna. Okay, yeah, I'll be quiet.
So we also include the hash of the previous block in the block. So, and I should mention that the hash, when we calculate the hash of the block, we include all the information in the block, including the hash of the previous block. So if anything changes in the previous block, its hash changes, and therefore the hash of this block also changes, right? So, and they have timestamp, maker root, don't worry about it for now. We talk about it later. Miner is the label that we give to the person who actually inserts the transactions and organizes these and gets the fee. So this fee is paid to someone. We call that person miner for now, okay? And forget about nodes for now, but what foreign keys do we have in this table? Can someone tell me? We have two foreign keys in this table. Which are they? Which columns are the foreign keys in this table? Can you guess?
Which table are you talking about?
What?
Which table are you talking about?
Blocks table.
Okay. A foreign key. The previous hash.
Okay. Points to the hash of the previous block.
Primary key.
Okay.
Yeah.
What other?
Oh,
The miner. The miner is an account.
miner.
The miner is an account.
So the account holders do the mining.
Yep. A miner is one of the account holders.
Oh, okay.
So an account can be the miner for no block or multiple blocks. But a miner must be an account. Okay.
So how is previous hash a foreign key if it's not pointing at a primary key? You said it was a primary key.
That's a good point. So here we have the previous hash foreign key pointing to the block hash. Okay. So remember when I told you that the foreign key points to a primary key in another table? I lied. So it doesn't always. It doesn't. So the foreign key can point to any column that is unique and universal. It doesn't have to be the primary key. It should have it should be a candidate key. You know, it should be candidate key, which is the case here. The block hash is a candidate key. Okay, and and it doesn't have to be in another table. It can be in the same table. So it is a self-referencing relationship. Okay, so this means that each block is pointing to its previous block. Essentially, each block stores the hash of the previous block and includes the hash of the previous block in itself. So if you change anything in any block, it changes the hash of its hash and the hash of the next block and the hash of the next block. So the hash of all the blocks after that will be invalid, and you can detect it. So you cannot change even a bit in any block without just destroying the whole database. So essentially you have a chain of blocks or a blockchain. Okay?
Well, just curious, because I read about the blockchain.
If we store the balance, it would be like Ethereum. If we don't store the balance and compute the balance dynamically every time, it will be different.
So it's like how much Bitcoin I have?
Yeah, exactly. Your balance of Bitcoin. Exactly.
So if I'm interviewing for a position, do I have to recommend that they have the blockchain in every database?
No, not at all.
No?
At all, not at all.
Okay.
So it is just a demonstration.
This is like questions I get.
It is just a demonstration, so you learn about databases and blockchain at the same time. So
Is blockchain going to be on the exam? Blockchain table?
yes,
Yes, it is.
definitely.
Yes. Okay.
So I should mention that the accounts table.
Guys, don't make me come down there. Seriously.
So the accounts table is not necessary to be here, probably, but we can keep it, we can drop it, because we only need the public key of each account. So now I'm gonna try to, how much time do I have?
So you have about like 7 minutes, yeah.
7 minutes, yeah. So I have implemented this database. You can go to this GitHub address and just see the code. So there is a lot more to it. There is mining, there are security measures, there are many other things. And if you want, so if you use Lucidchart, you can get the code for building the database like this. I choose SQL Server standard, and it generates the code for you, and you have the code. So this is the code. Unfortunately, what it generates is unfortunately what it generates is very basic and simplified. It just creates tables and not much help. But we need a lot of other things in our code. So
Students know that.
Don't tell them.
here,
Don't tell them.
if you see
Can you use that site on the exam?
what?
Tell them too, because I'm
She said, can you use Lucidchart on the exam?
Yes, absolutely.
Of course you
I
can.
can use
Yes,
Lucidchart, but I
of
don't.
course.
Oh, she also said for us to tell you that we never let anyone finish, so don't worry about it.
Oh, okay. So here we have the tables, definition of the tables. This is, you don't need to remember, you don't need to memorize syntax at all. You can always look it up. You will have access to internet during the exam. Don't worry about it. So here I am creating the tables or defining the tables, the 4 tables that we have. We designed the tables. I should mention some important thing here. I'm granting access to everybody to read from the database. So the select command is essentially reading from the database, and everybody can read any information from the database. It's publicly visible, as promised. However, I am revoking update and delete access from everybody. So nobody can, can you see that?
Oh yeah.
Barry.
So nobody can update any information in the database or delete any information from the database. This is the difference. This makes this database tamper-proof. So this makes it an append-only database. You can only add to this database. Okay? And so we grant insert access. Anybody can insert new information to the accounts table and the parties table. However, to add new information to the blocks table and the transactions table, they have to go through the procedures that we have. So the procedures that we have enforce the blockchain protocol. So we have a protocol, and the procedure enforces the protocol, and we have of course, the procedure here. We have several procedures and functions, and if you want, you can just go to this GitHub, and you can just see the code, play with it, make some blocks, actually mine some blocks, and see how it works. So it's very helpful to understand how blockchain works and also how database works. Okay, so any question?
Anita has a hand up.
Okay.
Yeah, I was reading about this really cool thing called quantum computing.
Okay.
And it was going to change the ability for me to, manipulate some of the security that they put on things like you've described today. Because, we talk about how it's not, people can't tamper with it, right? And I'm guessing that that's based on the algorithms that we use today for security, but will quantum computing sort of change what we have to do as we go forward to try to keep databases tamper-proof?
Absolutely.
By the way, totally unfair question, but you're going to get the question.
Yeah, absolutely. That's actually a great question. So remember the public key and private key that I mentioned? So the process is that you start with a private key, you build an equation whose answer is the private key. We call this equation the public key. And then you know the answer to this equation, and you are the only one who knows the answer to this equation. And nobody can solve this equation in a reasonable time. So, for example, for Bitcoin, it takes I think millions of years to find the private key from the public key, essentially to solve the equation. To solve this equation, we have to try out each potential private key into the equation, plug it in, and see if it solves the equation. And then try the next one. There is no systematic way to solve this equation. So we have to just try out one, next, and until we find the right answer, the right private key. And it takes millions of years. With quantum computers, we don't need to do that. With quantum computers, we try out all the possible private keys at once. And we see for which one the equation is solved. And the equation is solved for one of the private keys, and then we know which one is actually the correct private key. Essentially, we can solve the equation in a matter of seconds. And that means we can easily find the private key from the public key. And that means we have access to everybody's account. We can transfer anybody's money without their permission, and we are all doomed. So that is actually Bitcoin.
Thank you very much.
Sure.
That was a good way to answer that. Thank you very much.
But
Sorry
I
to
should mention
interrupt
that
you.
there are measures there are some good measures that they are taking in Ethereum, Solana, and other blockchains. Unfortunately, they cannot do anything about Bitcoin. It has no governance mechanism. Nobody can change anything about Bitcoin. But for other blockchains, they are taking measures against the quantum computing.
So thank you so much for Danielle. Yeah,
Sure.